Okay, so we're going to talk about time and the Earth, Moon, Sun cycles today. We'll start off with discussing the difference between sidereal and synodic time. And perhaps we'll start off with a few key points just to remind yourselves about what we're up to. So firstly, of course, 1 year corresponds to one complete orbit of the Earth around the Sun. And during that time, the Earth spins on its axis 365 1/4 times. Now, one sidereal day corresponds to the time taken for the Earth to spin once on its axis. It's equal to 23 hours and 56 minutes, and you need to know that. Okay? But one solar or synodic day is 4 minutes longer, that's 24 hours. So the synodic day, 24 hours, the sidereal day, 23 hours and 56 minutes. Right, and if you should know the sort of dates for the equinoxes and the solstice. So the winter solstice, December 21st, and the spring equinoxes, the March 21st, and the summer solstice is June the 21st. Okay, and in the autumnal equinox, September the 23rd. Okay, now for the equinoxes, the sun, of course, is above the equator. For the winter, the sun's above the Tropic of Capricorn, and for the summer, the sun is above the Tropic of Cancer. Okay, so over this diagram we're looking at, I'll explain what I mean by that. We should also remember that ignoring precession, the Earth's axis of rotation remains fixed with respect to the stars, but it is not fixed with respect to the Sun. And during one solar orbit, the Sun lies directly above key latitudes on key dates, as I've just discussed. Now, the Earth's orbit around the Sun and its fixed axis of rotation explain why the Sun rises and sets at different times on different dates during the year. It also explains the apparent motion of the Sun on the celestial sphere and why the altitude of the Sun and Moon is different on different dates. Now, close to the spring and autumn equinoxes, the days and nights are roughly the same length. Of course, we know the word equinox suggests that anyway, doesn't it? As spring advances, the days become longer, with the times of sunrise and sunset being gradually earlier and later in the day. The sun rises at its earliest and sets at its latest times on dates close to the summer solstice in June. In December, close to the date of the winter solstice, and the reverse is true. In the southern hemisphere, the opposite applies. Days are longer in December and shorter in June, as you'd expect. Okay, so you certainly need to know the dates for the equinoxes and the solstices, and I'd say you need to know those the differences in length of time between a sidereal day and a synodic day. So let's just now discuss the lunar phases. Okay, I'm putting a picture now of the sequence of images which show the lunar phase cycle, and this is actually one of our tasks that we're supposed to have done, our practical tasks. Okay, now although one sidereal month, the time for one complete revolution of the Earth, is equivalent to 27.3 days, one solar or synodic month, the lunar phase shown, is 2.2 days longer, that's 29.5 days. So a sidereal month is 27.3, but a solar month is 29.5. And the reason for this difference is that during the time taken for the Moon to complete one orbit of the Earth-Moon system has moved through an angle of 27 degrees in its orbit around the Sun. So have a look at this diagram on the screen at the moment, and I'll just try to explain what the diagram is telling you, okay? So at position M1, the Moon is aligned with the Sun and the Earth, and it's a new Moon. Now, during one complete orbit, that's 27.3 days, the Moon has moved from position M1 to M2. Okay? Now, during this time, the Earth has removed significantly in its solar orbit from E1 to E2. So an extra 2.2 days are needed to realign the Moon, now at M3, with the Sun and the Earth once more. All right. I have made other videos on that, so please do look those up too. Sundials and shadow sticks is also we need to discuss. Okay, so sundials use an opaque object to cast a shadow of the sun, as you know. In the case of a sundial, the object is traditionally a metallic triangular gnomon, that's spelled GNOMON, okay, with slanting edge points to the North Celestial Pole, the NCP. The shadow is cast onto a horizontal plate that contains the graduated scale from which the time can be read. Sundials have been used to tell the time since antiquity. When correctly aligned, they indicate apparent solar time, AST, apparent solar time. However, whereas our phones, watches and town hall clocks tick even by the same amount every second of the day, the sun does not oblige us with such regularity, and on some days the sun moves more slowly across the sky, on others it moves more quickly, for reasons we shall see soon, but of course you know that the Earth is on a slightly elliptical orbit. So in the days before we had such timekeeping devices, a correction had to be made to the apparent solar time as indicated on the sundial in order to obtain the mean solar time, MST, the mean solar time for a particular location. And this was based on an imaginary mean sun that did cross the sky in a consistent manner. And remember, that's not finding Greenwich Mean Time, that's finding the mean solar time. The correction is known as the equation of time, EOT, and its value, and this can be negative as well as positive, differs for different dates of the year. So I've put an example of an equation of time graph on the screen now. Now the equation of time is equal to the apparent solar time, AST, subtracting the mean solar time, MST. Okay. Now, when the EOT is positive, we say that the real sun is faster than the mean sun, and when the EOT is negative, we say the real sun is slow. So using arithmetic, if a sundial reads 10:45 on a particular day of the year and the EOT for that date is minus 5 minutes, then the mean solar time is 10:50. Because obviously subtracting a negative is like adding, isn't it? As the name suggests, a shadow stick often uses a vertical, wooden circular and a reasonably thin stick, such as a 1 centimeter diameter dowel, often placed in a bucket or a plant pot or sand or gravel to cast its shadow onto a large horizontal piece of light-coloured card. It can be used to determine the time at which the sun culminates at local noon and the observer's longitude. As the sun rises in the east, culminates when due south and starts to set in the west, the length and direction of the shadow will change. So I'll put in another diagram, hopefully that's self-explanatory. We might be able to find time during the year to do an experiment on this, but basically the tip of the shadow should be marked with a very small cross, say every 5 minutes for about 10:30 until 13:30. I have to be careful about daylight saving time, of course, and together the time indicated by a phone or watch. Okay. Right, once the length of the stick shadow at different times around the local noon have been found, a graph of shadow length against time indicated on a watch or phone can be plotted. It's important that the shadow length axis does not start at 0, since the curve will be very shallow, but avoid zigzags if we can, and this will make it difficult to judge the lowest point on the curve. The graph should be a smooth curve, don't just join the dots up, from which the time of the shorter shadow can be read off on the time axis. The graph indicates that this occurs, for example, here on the screen at 11:52 GMT. So, let's talk about now the equation of time. And again, I have made previous videos on this, okay? In addition to tables and graphs, such as the one we just looked at, the OT can be read from an analemma, spelled ANALEMMA. This has been likened by many students to a wobbly snowman, okay, and shows how the EOT varies with month of the year and also the sun's decimation. Charts, graphs, and analemmae show that from late December until mid-April, the EOT is negative by up to 14 minutes. The sun in the sky is slow compared with the mean sun. And from mid-April until middle of June, the EOT is positive by up to 4 minutes from the fast sun. From the middle of June until the beginning of spring, the OT is negative again by up to 7 minutes. The sun is slow again. And from early September until late December, the EOT is positive by up to 17 minutes. The real sun in the sky is fast again. Okay. Now earlier we introduced the concept of the mean sun, which forms the basis of civil as opposed to solar timekeeping. The mean sun moves across the sky, and more precisely on the celestial equator, at a fixed rate every day. The real sun, however, moves up and down along the ecliptic at different rates, and so the annual variation in the EOT is due to two factors: the Earth's elliptical orbit. The Earth travels at different speeds in its orbit, causing the real sun to move slower or faster in the sky on different dates, and the tilt of the Earth's axis, or obliquity of the ecliptic. That's the proper word, okay? So the tilt of the Earth's axis, or the obliquity of the ecliptic, close to the solstices. The real sun is travelling faster from east to west than close to the equinoxes, when a large component of its apparent motion is northwards or southwards, and the sun therefore lags behind and leaps ahead of the mean sun. Yeah. So if we go back to the idea of that shadow stick experiment we were talking about earlier, to show how the data can be used to determine longitude. Since the shadow data was obtained using the real sun in the sky, then the local apparent solar time of the shorter shadow was 12 noon. We can now use the equation of time to convert AST into local MST. This is also known as the local mean time, LMT. Let's say then, on the date that we obtained the data, the EOT was plus 12 minutes. Now, since EOT is equal to AST minus MST, we can rearrange that equation to get an equation where MST is the subject, and that's going to be 12 take away 12 minutes equals 11:48. So the local mean time was 11:48, and yet the local mean time in Greenwich was 11:52, 4 minutes later. Remembering that the Earth rotates on its axis by 1 degree every 4 minutes, this means that the difference in longitude between when the experiment was carried out and Greenwich is 1 degree. Since local noon occurred 4 minutes earlier than at Greenwich, the longitude from where the experiment was carried out must be west of Greenwich, longitude 1 degree west. Okay, before rail travel became popular in the second quarter of the 19th century, local mean time was used by all people. Unfortunately, local mean time differed from city to city because the sun crossed their meridians at slightly different times. This caused a huge problem for railway timetabling until 1847, when the railway companies agreed to use a standard time for all rail journeys. Finally, in 1880, a government legislation standardised time, local mean solar time at Greenwich, or Greenwich Mean Time, for the whole of the country, albeit not without strong resistance from some towns and cities. Of course, when you look at a picture of a map, a world map showing the different time zones. Since the Earth rotates by 15 degrees in 1 hour, time zones are roughly 15 degrees wide, and almost adjacent zones differ in time by 1 hour. There are, however, many exceptions to this generalisation. Presently, other countries followed suit, and we now have a world split into time zones, the majority of which are nominally 15 degrees of longitude wide, with most adjacent zones differing in time by 1 hour. Okay, although of course we do have half-hour gaps. Okay, By the way, I haven't mentioned, but I saw a couple of years back. There's a book called Finding Longitude, and I really strongly recommend that you read that. It's very interesting, and it sort of explains the importance of accuracy of clocks and why they're needed in the race to find accurate longitude readings. The 17th century witnessed a rapid expansion in the number of sea vessels exploring or conquering new territories, waging war and trading gold, silk, spices, etc., etc. And whereas latitude could be determined easily, even from the deck of a rolling ship, by measuring the altitude of a particular star, such as Polaris or the Sun at local noon, longitude always posed a huge problem for the seafarers, and this inadequacy resulted in numerous shipwrecks and many fatalities. And in 1675, King Charles II founded the Royal Observatory in Greenwich with the intention of solving the longitude problem. He learnt that a Frenchman named Le Sieur de Saint-Pierre had resurrected an earlier proposal by German astronomer Johannes Werner to produce detailed maps showing the position of the moon at different times and on different dates at some key port. Now, the intention was that the port's longitude would act as the 0-degree reference point. This lunar distance method allows ships navigators to deduce the local times aboard ship by observing the stars and at its home port using the maps. The time difference could then be equated to the ship's longitude. Unfortunately, neither the positions of the stars were well known nor the motion of the moon was fully understood. However, the longitude problem was not long from being solved by astronomers and clockmakers. In 1761, after many trials and tribulations, horologist John Harrison, you need to know that name, John Harrison, solved the longitude problem with the invention and production of the marine chronometer that kept accurate home port time aboard ships sailing in the most extreme conditions of temperature, humidity, and salinity. And if you ever get to see one, that's really something quite special. Okay, a John Harrison clock solved the problem of finding longitude.